Lect31 E524 digital MOS LSI circuits, and today is November 3, 2020. So we were talking about very crucial circuits which is used in all the digital circuits known as the multivibrator circuits. So in multivibrators, we have learned about three crucial elements: monostable, astable, and bistable circuits. So in the case of monostable and bistable, it requires input. However, in the case of astable, input does not require. Right? We also learn about comparator, like inverter is a comparator, and inverter's characteristics, so that it can be used as a Smith trigger. So Smith trigger is the one which has like two switching thresholds rather than only one. You know the advantage of that, which is the previous lecture, right? And generally this is a positive feedback circuit. We have also studied op-amp based circuit, or making a dynamic latch circuit, which is going to be the comparator. And there is another circuit which looks like this one. You can see over here there are three inverters, but the first inverter is composed of M1 and M2, and second one is here. So there are two inverters back to back. However, the output is connected to the second inverter through one another inverter, you can say, right? Or you can reconnect this. If you want to do this one, you can do this one also, right? It's same, connections are same. So in this case, what is going to happen if this is Vin equal to 1, this is equal to 0, and this is equal to 1. And another way around, you can say that if this is 1, this transistor is off, and its counterpart, this one is on, and of course this is going to be equal to 0, right? And opposite will happen when it is Vin equal to 0. You can derive the thing which is going to happen. However, the main conceptual thing is when this is going to make the switching from 1 to 0 or 0 to 1. So we are interested in this kind of curve, right? When you are traveling from 0 to 1 and maybe coming from 1 to 0, what is going to happen? So here you can see that when you are going from, let's say, 0 to 1, as this is two inverters back to back, it's actually a buffer circuit, right? And it's not going to be the inverted, but it's going to be like this. But what if you are actually at this point, if you are somewhere here, like I would say that if you are somewhere here where the flipping is going to happen, right? At that time, it's all depends on two things. What is the value of PMOS and NMOS, so that it allows the transition over here. Otherwise, that transition won't happen. What I mean to say, if M1 and M2 are minimum 1, or you can say that the regular sizes which you are doing, like 130 nanometer L and maybe 100 or 200 nanometer of width in M1 and M2, same for this one. But if I am making these transistors little bit, I would say that little bit stronger or weaker, such a way that it's going to change the noise margin high and noise margin low. I am doing this because these two are the points which are going to be acted over here as switching threshold 1 and switching threshold 0, right? So if you want to do that, what you can do, you can make the relatively value of W by L of M4 and M3 such that these are not going to be tuned immediately what you want, right? I want to say that if Vin equal to 1, or you can say that approximately 1, we are somewhere here, or maybe here, let's say. So if this value is here, Vm plus and Vm minus. So if Vm plus you are giving, then the other side will be little bit away from this point, right? Sorry, in that situation, you might have some value which is digital logic 1 or 0, or some value will be here depending on what you are giving. So here this will be this value. Let's call it Vx. If Vx is here, for a given Vx, what will be the V out? So in that case, we need to check accordingly, right? So where you are moving over here and what value of Vm plus and Vm minus are driving over here, that is going to be decided by these two transistors now, M3 and M4, right? So if M3 and M4 are pretty high, what is going to happen? And if it is low, what is going to happen? That you have to understood. So let's assume that if they are very big as compared to the W by L of the given W by L of this inverter. In that case, what is going to happen? If this is logic 1, let's assume that near to logic 1, these are very strong. They are not weak. Both are very strong when W by L are very big. In that case, resistance is very small, right? So if resistance is small, so quickly they will charge or discharge this node. We don't want that. We want that they are charging or discharging such a way that it's it changes with this Vm plus and Vm minus. So accordingly, for a required noise margin values, you can make the W by L of M4 and M3. And similarly, you can also think about a circuit which is again under Smith trigger. By the way, this is a question given in Rabe that you have to find out the Vm plus and Vm minus. Its solution is also given at the back of the book. So here also you can think about this circuit, how it's going to work. I'm not going into that. However, by feeding the value of input from 0 to VDD and check when it's coming from VDD to 0, whether it's giving you this one or not. If no, then why? You need to find out. Right, so this is what we want. Now the next one is the monostable or mono short circuit. So this circuit is also very famous, and it's going to give you the mono short, or you can say that it's only pulse which is going to be on for small period of time, or maybe you might have the reverse also. It depends up to you, like whether you want going towards logic 1 or logic 0. So if it is this kind of circuit which you want, then you can design a delay element. By the way, delay element is nothing but you can design even number of inverters which with whatever the value is required. If you remember, one single inverter is going to give you 0.69 Ron of P times whatever the capacitance at the output or the total capacitance, right? Let's call this one as C total on P, or maybe R on N, depending on what value of resistance is there, right? So accordingly, you can design the value of delay, and that delay, when you are keeping on the input line, you can see that if this is the input which you are feeding, and if this is Vx point, if I am drawing the Vx point, if it has a delay of TD. After TD, it's going to be on for forever until we are not changing this one. So in that case, because of this XOR operation, the output is going to be 1 when are not equal. If both are equal, then output is 0, right? So as it is known to us, so this is how it looks like, and this is creating a mono-short circuit. So this is one of the example. However, you can have many other circuits through which you can design a monostable circuits or the mono-short for a given uh, I would say that time of making it on or making it off, right? So this is called monostable or the mono-short. The third one is very popular and it's known as the voltage controlled oscillator. It's known as the voltage controlled oscillator, and I'm going to make the astable multivibrator circuit. What astable multivibrator is going to do is as follows. You can have odd number of inverters and keep it in negative feedback. Look at this. This is a negative feedback. It's a negative feedback. Odd number of inverters, and it's a negative feedback. Note that this particular circuit, when people used to make, they are making mistake, or they are not able to get the oscillations, because the oscillation is the important point over here. If you want to have the oscillations, actually there is a some oscillation theory. It's only working with the, if you're keeping it in negative feedback, it has to follow the Barkhausen criteria, through which it is going to give you the oscillations. So for separate course called mixed signal VLSI design, where I have explained how this Barkhausen criteria is derived and various oscillators has been checked, and its oscillatory condition and its frequency, those has been derived there. But if you are interested only in digital logic 1 and digital logic 0, and the simplest one is the voltage controlled oscillator, where it's also known as the ring oscillator. Right? So in ring oscillator, keeping odd number of inverters, it's going to give you the oscillations over here or here, wherever, like you can see. Note that the number of required inverters are more than 1. If you are keeping 1, it's not going to oscillate. By the way, that is one of the question given in the assignment, that 1 is not going to oscillate. You can check that whether it's oscillating or not. Note that I don't know, I haven't used Simica for ring oscillator and all, but if it is not oscillating, if by mistake if it is not oscillating, I suggest to give some initial condition to start. Okay, give some initial condition, that might be helpful. Okay, so these ring oscillator will decide that what is the frequency. So if you remember, long back we have talked about it. If there are 3 inverters, if I am keeping it back to the input side, if this is positive, this is negative, this is positive, this is negative, so this is a negative feedback circuit. When I'm going to do this one, the output, okay, maybe it will start with some small oscillations, and then you will see the logic 1 and 0. So you have to give the enough time so that the oscillations will be converted to the large scale value, which is VDD or ground. And here the frequency is depending on one fact, that what is the propagation delay from this point to this point. You can see if all are identical and having the propagation delay of TD, then this would be 3 TD, right? So that's the propagation delay, and you can find out the frequency of operation of 1 by 3D, right? So by the way, multiply by 2 pi, right? Otherwise it's in a radian per second. So when we are doing this, if you want to increase or decrease uh, the TD coming from each stage, then you have to touch the W by L, right? So if you are increasing W by L of N and P, you are going to have better and better resistance, or I would say that resistance value is going to be decreased, and that RC time constant is going to give you the propagation delay, right? Going from low to high and high to low. So in that case, if you are keeping very high value, you are going to get better number, right? And you might achieve 1 giga or maybe or more than that if it is required, right? However, as you are increasing this, what is going to happen? As you are increasing this, what will happen to the current? So we know that the current is nothing but mu n Cox by, or we can write down right, Kn or Kp, anything will be here, right? I have written only for the current for the drain to source in the case of NMOS, right? So as you are increasing W by L, look, this Kn is also increasing, and you can see that this is also going to increase. Overall, you are going to have very high IDS. If you want to achieve a high bandwidth or the high value, in that case you need to increase current. So there is no other way, right? So other than that, there is a technique called current starving VCO, where you have the current starved inverters are there, in which you're going to keep one V control over here, which is going to tell me that how much current is required as a reference one, right? And because of that, whenever there is a control voltage is there for a given control voltage, how much current is required, that much current is going to flow from here, not higher than that one, right? And accordingly, that much bandwidth can be achieved over here, right? So that is the another class. Third one is you can have delay cell and VCO. So what you can do, instead of look, 3 stages of inversion here also, like we are making 3 stages of inverter, but we are making the latch circuit, which is going to give you the delay also. So here there is one block. By the way, this block is actually known as the GM block. GM is the one when output is current and input is voltage. So as you are increasing voltage, I want to increase current also. If I want to have this one, the easiest way is, if you know the small signal model. So if this is small signal voltage, it's GM times VGS, which is going to be increased at the output side. So that is what I want over here, and I'm doing that as V in is increasing, then V out is also, like, current is also increasing, or V out is also increasing. So in that case, if in plus and in minus are differential, and if this is 1 and this is 0, accordingly it's going to make the other circuit on and off. And you can see that VO plus and VO minus are going to make the flipping. However, just having one cell is not going to help you too much. But if you are going to have two cells, which looks like as follow. So let's call this one as another I plus and I minus, and this is going to be here, this is going to be here. Okay, so the first block is the red one, so I plus. In that case, this will be O minus, and this will be O plus, right? O plus is connected to I minus, and O minus is connected to I plus, and this O plus, like VO plus and VO minus, are connected to plus plus side. So you can see over here, they're making the connection like this, right? So in that case, actually, when it's making, if you are looking at the delay cell and looking at the circuitry, effectively, these are two inverters. These are two inverters, right? Whose input and output are cross coupled, right? So plus is connected to the another one and minus is connected to another one. So these are the two inverters, and this one is connected to the next guy. When you are doing this, what is going to happen over here? So if you are looking at just one output at a time, actually there are three inverters effectively, and because of three inverters you can see the oscillations. So that is, so first circuit was just a latch which is not going to change the state. However, if you are doing this one with the cross coupled, means the astable multivibrator configuration, it's going to give you oscillation. And that was the last thing for the sequential circuits. So that completes the whole chapter, right, without missing any topic. The memories, so this is CMOS memories which we are studying, by the way. Yeah, as the title of this course is Digital MOS LSI, we are not moving here and there, not other kind of memories, but we are talking about just CMOS memories. For this particular topic, I'm going to change the book to West and Harris, which we have studied for logical effort also. For that, you should refer the chapter number 12 of this book. By the way, same chapter number 12 of Rabe book is also very nicely written by Rabe. You can follow that also. But considering the fact that it covers more things in terms of memory organization, they start with memory organization, and then he's teaching on other things. So I didn't want to go to the memory organization right now. So if you are, so I believe that you all know how the memory is organized, and things are designed for that computer architecture things, because on computer architectures and the required specifications, we are going to design directly to SRAM, DRAM, and other things, right? So that is what we are going to talk with, and it's going well with the chapter given in this particular book. So I like that. So I'm, for this particular chapter, I'm going to follow this book only. However, I would also recommend that you can read this book also. This book is also very nicely written. There is nothing is, I would say that it's all about your understanding, right? If you can follow, like I have studied both the books, and I like both the books equally. This is all about like these topics are one by one kept such a way that I can teach you what is required. That's why I'm choosing this. So let's start with the memories. So in memory arrays, you might have studied all these things, but just I'm for rephrasing the thing, I can tell you that there are mainly three kinds of memories. One is called random access memory, RAM. One is called serial access memory, and one is called content accessible memory, or CAM. By the way, under the RAM, there are two kinds of memories, volatile and non-volatile. You can see here with the time as it has been evolved, this name becomes RAM. It's also random access memory. They wanted to write it down random read write memory, but later on it has become RAM only. However, actually this is read only memory, and this is random access memory, which can read and write both. So, but RAM was the original name over here. Hierarchically, it was one level up. And volatile memories and non-volatile memories are the popular names, and people are also knowing the memories with these names. Mostly all the companies has these teams which has uh, like SRAM, DRAM, and NVM. NVM is non-volatile memory, so this is also known as NVM in many companies. So it's very popular topics of study because it gives good opportunity in the market so that you can have good job for memories, because memory division is everywhere in every company. So either you go to TI or you go to ST, you go to Freescale, Qualcomm, right? All have memory divisions, and these are the names of the memories. So let's look at these memories one more time. So you know that random access memory has two things, volatile and non-volatile. In serial access memories, note that this class of memory is dealing with two things. It's not only remembering the data, but it's remembering the data at a given address. So there are two things. It's also remembering the address and data. It's not only one thing. For a given address, data is stored over there. However, serial access memory, it's accessing the memory or reading, writing, whatever it's doing the sequentially. So it does not require any kind of address, right? So it's all about data. This and this, all about data. However, this CAM is the content accessible memory, which is going with some special keys. So it matches the keys. If it is there, it's going to find out whatever data is required. So it's all about these memory arrays, where one is RAM, which is address and data based. One is serial access memory, which is sequential based, or you can design these kind of memories using a proper sequential circuits like shift registers, queues, like SIPO, PISO, FIFO, LIFO, right? So you must have studied these things in previous courses, right? So these are very much important in computer peripheries, and these are working sequentially, right? Sometimes with like it might be synchronous, it might be asynchronous, right? So that is how you can design this, and this does not require separate understanding, right? That can be done the way you have done it for all the sequential circuits. It's an extension of the sequential circuit only, right? And CAM is the content accessible memory, which requires, of course, it's also one of the useful memory which is being used, right? So but our main thing will be focused on this side, which is random access memory, where you might have volatile and non-volatile memories. So non-volatile memories, we are going to refer it as NVM from today. Okay, so that you have to understand that NVM is non-volatile memory, and you with name suggests that it's also read and write, and volatile non-volatile cannot read and write, so it's only the read-only memory. In the case of volatile memory, you might have two different memories, like the case of the static and dynamic. If you remember, in sequential circuits, we had static circuits and the dynamic circuits, right? So it's similar to that. Static RAM is the one which is your data is not going to be lost immediately until and unless you have the power up is there. This is going to be there. And in the case of dynamic RAM, where you have some sort of switch caps or capacitors are there, where the data is going to be stored, so that particular data needs refresh, or you can say that sometimes if you don't refresh it and for the longer time, it can also get discharged. So it requires the frequent changing of the data on capacitor. So that is the DRAM, right? And in the case of non-volatile memories, notably, this is also given in the book, and that's the next slide I copied also. That non-volatile memories are not completely non-volatile. It can also program, it can read and write also. Okay, so it's not completely just, you can say that non-volatile. You can read write also, but it depends on different conditions. So the first class is the mask ROM, which is having the fabric. It has been fabricated with the hard wires, and look, afterwards you cannot change it, right, every time. However, the programmable ROM, you can program it with some kind of fuse are there inside the memory. This is also one of the old class of the memory where people used to do that. Still people are using some places. However, uh, these are the programmable by the hardware things where the fuse are there, right? And similar to that, if you know the programmable logic array, and nowadays like field programmable gate array are there, where you can reprogram it with some switches given inside that particular board. So it's similar to that, but it requires the hardware where you're going or changing it physically over there. But there is one more class of the programmable ROM, which is erasable programmable ROM, where what you are doing for a certain time of time, you are going to give ultraviolet rays on the circuit, so then the data will be erased. And there is one more, which is electrically erasable programmable ROM, where you can erase it with the electrical like electrical activity, or you can design it such a way that it's going to give you like it can erase the data. But there is one more ROM, which is generally known as Flash NVM also. This is very popular in design, and in that the circuit has to be changed a bit, or you can say that the transistors might be CMOS, but it should have some floating gates will be there, which can remember the data, and you can erase it electrically only. It's extension of this particular EE PROM only, but this is very popular in last decade, and you can say that flash NVM is actually similar to what the volatile memories are. It can be like it's extension of that only. Some people are also this one. Anyway, so let's look at that what this book is talking about. So random access memory is accessed with an address and has a latency independent of the address. Okay, in contrast of the serial access memory are accessed sequentially, so address is no address is necessary, as I told you. And content as addressable memories determine which addresses contain data that matches the specified key. So that's going to be the content addressable memories. But if you are looking at RAM, which are read and write both, so uh, RAM is like, as I told you, NVM, flash, and many other memory which are non-volatile. Sometimes these kind of RAM is becoming synonymous to volatile memory, while ROM is synonymous to non-volatile memory. But still, things are getting evolved, and non-volatile memory is also going towards the writing side also, right? You can erase it, you can rewrite it. Now, if you look at the memory um, at the top side, so what I'm doing here, let's assume that there are 4 blocks are given in this particular row, and 4 blocks are given in the column like this. And each one of them has some address. Let's call this one as 00, 01, 02, 03. By the way, these are the decimal numbers. I'm just giving you example. 10, 20, 30, right? 11, 21, 31, 22, 23, sorry, 2, 22, and 32. This is going to be 13, 23, and 33. Now, all these are some of the circuits. 0001, all are the numbers. Now, let's assume that I want to write something on this particular circuit, I want to write down something inside this, either digital logic 1 or digital logic 0. Note that each one of them might be some memory elements, right? So for that, what I'm doing, I'm keeping here some horizontal lines. Look at this. And I'm going to keep some vertical lines which are going to be controlled by this red color box and the blue color box. What this red color box is going to do, this red color box know that I'm supposed to write somewhere here inside this. So in that case, if it knows that, so by the way, these are connected like this. And all other things are connected like this. So it's a big matrix over here. Now, if I want to write or read something at this circled circuit, then what I need to do, I need to make sure that this has to be digital logic 1. This has to be digital logic 1. And at the same time, this also have to be digital logic 1. Right? When it's, note that when you are doing this, this horizontal line makes connection with these three. This particular guy does not know that which is going to be the value I'm going to read. It's going to be determined by this vertical line where it's making the connection with these four, right? So the common one is this one, and that gives me access to this particular part of the memory, right? So each one of them is one cell. So each one of them is known as one memory cell, which I'm going to access it, or I'm going to read, or maybe I can write it down, right? It might be any memory. Look, as this topic suggests that it's a memory, it might be any memory. It might have different specifications, but all memories are going to have the same architecture at the top level. So, by the way, you might be able to understand that this particular structure is known as 2:4 decoder, right? And this is also 2:4 decoder for the given circuit. It might be other number also. It might be 3x8, or you can say that n×2n decoder. By the way, this vertical one, which has the red color, it's taking care of all the rows. That's why we are calling this particular decoder as row decoder. And this one, I'm going to call it as column decoder. Now, if you are supposed to design a decoder in row or column, what you need to do, you can design it with the logic gates, right? It might be with the NAND gate, or it might be with, so whatever the circuits you have studied in your digital electronics course, same circuit will be here, but you have to design all the gates also. So the project which I am going to give you, that project needs to design all these memory cells. These memory cells are identical to each other. First of all, let's understand this. And these decoders you have to design. And other than that, there is something called sense amplifier, which will give you the logic 1 or logic 0 value at the output. And that is required some attention, right? So that is what we are going to study. But you can see same thing over here, where The row decoder has 16 line this side, so it's 4 is to 16 decoder, and this side it's 2 is to 4 decoder. Same thing can be designed with the fact that this side you can have 3 is to 8 and 3 is to 8 decoders, which are going to decode the value which is required. By the way, all the horizontal lines you can see coming from the row decoder are going to be known as word lines. All these horizontal lines are known as word lines, and word lines are going to tell you the address, by the way. Notably, you have the vertical lines which are going to be known as bit lines, and it's all talking about the data, right, which is written over here. So bit lines and word lines are there. Notably, it's not only bit lines, you will have also bit line bar also.